All right, welcome everybody to part B of chapter 11 over the fundamentals of nervous tissue. And what we're going to be looking at today is a little bit about how it is that nerve signals are actually produced. Okay, so neurons and muscle cells are an example of what are called excitable cells. They can respond to a stimulus by generating a special kind of electrical signal that's called an action potential, which moves at one speed, one direction, and one magnitude from where it's produced to its destination. Okay? Once an action potential is produced, there's no way for it to stop. All right? And the reason that action potentials can be generated on the membranes of muscle cells and the axons of neurons is because of the composition of the membrane in those particular cells, which allows action potentials to be generated and propagated. Other regions of the nerve cell, such as the dendrites and the soma, don't have this capability because they don't have the proper membrane proteins to produce an action potential. Okay? Other cells in the body can't produce action potentials because of the lack of these special membrane proteins that are designed to respond to a chemical stimulus and an electrical stimulus in such a way that we can produce this particular type of long distance signal. All right. So one of the things we have to appreciate is just like in magnetism, opposite charges will attract and similar charges will repel. And so the establishment of a property called membrane potential is important in the separation of these charges to serve as a form of what we call potential energy. Okay, so we're going to find out that every cell in the body expends quite a bit of ATP in order to keep these charges separated on either side of the membrane, such that the cell side of the membrane is negative compared to the extracellular portion of the membrane. In order to do this, we have to continually pump ions against their concentration gradients using ATP as a power source. This stores energy in the form of charge separation, which, when the separation between those two charges is broken, allows current to flow, which is the movement of charged particles, and that is a form of energy. Okay, you guys know it as current in an electrical wire when electrons move from place to place. Current in a living cell is when ions move from place to place. Okay, moving electrical charges. If opposite charges are separated, the system has this potential energy. Okay, and this is one of the ways that we can transform potential into electrical energy, right, by allowing the movement of these charged particles to take place. Voltage is simply the measurement of the difference in charge between two locations. This is known as potential difference or potential, and the greater the charge difference between 2 points, the higher the voltage. And in addition to that, the greater the electron motive force, the greater the electrical gradient, if you will, that will drive the movement of current from one location to the other. Okay? Current is just the flow of those charges between the 2 points, and resistance is the force that opposes that movement, right? In an insulator, the resistance is very high, and in a conductor, the resistance is very low. Okay, for instance, in the world that you know, right, with electrical components, metal is an excellent conductor. Okay, while something like rubber is an excellent insulator. Okay, the rubber has high resistance to current flow. The conductor has low resistance to current flow. Okay, in a cell, the resistance to flow is the result of leakage across the membrane. Okay, and the interference of current flow as a result of lack of surface area. Okay, so we'll specifically address those when we get to them. Ohm's law can simply be stated V equals IR. Let me write that up here real quick. Okay, we'll just do it in red, and V equals IR. So VIR. Okay, where R is resistance in ohms, I is current in amps, and V is voltage in volts. Okay. So current is directly proportional to voltage. No net current flow between points with the same potential is possible. Okay, because as the equation down here states, right, I is just rewriting that same equation above, is equal to V over R. So the higher the resistance, the less the current. The lower the resistance, the greater the current. The higher the voltage, the greater the current, and vice versa. Okay. So this is very much like fluid flow. You'll see something similar to this when you get to the circulatory system, where flow is equal to the difference in pressures over the resistance. Okay. So important to understand that in order for the current to move, there has to be a potential difference, has to be a voltage difference, and there has to be low enough resistance for there to be flow possible. Okay. So ion channels in membranes are of two types, right? You can have proteins spanning the membrane that are always open, and those are called leak channels. And you can have membrane proteins that span the membrane that have a door on them, and we call those gated channels. And the gates can respond either to changes in voltage, they can respond to the binding of a chemical, where we call them ligand-gated channels, or they can respond to some type of applied physical force, where we call them mechanically gated channels. So examples are shown here, right? Ligand-gated channels bind with a specific neurotransmitter latching onto them. Voltage-gated channels open and shut in response to changes in membrane potential, and mechanically gated in response to some sort of physical force. Could be pressure, could be stretch, right? Could be vibration. It all depends on what the modality is that that mechanically gated channel is going to respond to. Okay, so those are some of the examples. When gated channels are open, ions move quickly down their electrochemical gradient. They move along their chemical concentration gradient from high to low concentration, and along their electrical gradient towards the opposite charge. Ion flow creates an electrical current. That's the definition of current, right? The movement of a charged particle. And the voltage will change across the membrane when that happens. Potential difference across the membrane of a typical living cell is about negative 70 millivolts. Remember, milli is 1 times 10 to the minus 3. So this would be negative 70 times 10 to the minus 3 volts. Okay. So the cytoplasmic sign is going to bear the negative charge. The voltage difference can vary depending on where we are, from minus 40 to minus 90 in a resting cell. And in this state, we term the membrane to be polarized because there is a charge difference. Okay? When that charge difference becomes less, we call that depolarization. And when that charge difference becomes greater, we call that hyperpolarization. The establishment of membrane potential is the result of differences in the ion distribution in the intracellular and extracellular fluid, and the difference in the permeability of the plasma membrane. So you can see an example here how we would take a voltage, all right, with the electrode inside the cell and the ground outside, all right. And what you're going to see here in the video coming up is how that potential is established. Okay, you're going to find that the pump, the leak channels, and the fact that large anions are trapped inside the cell all play a role in establishing this membrane potential.
The human brain alone contains about 100 billion nerve cells, called neurons. A neuron, like every other cell, has positively and negatively charged ions, inside and outside. Further, a resting neuron has a greater negative charge on the inside surface of the plasma membrane and a greater positive charge on the outside surface. This partitioning of charge creates a voltage difference across the membrane known as the resting membrane potential, which can be measured using a voltmeter. On average, an intracellular electrode records a value of -70 millivolts. The resting membrane potential depends on two factors. First, it depends on the presence of sodium and potassium gradients across the plasma membrane. Specifically, there are more sodium ions outside the neuron than inside, and more potassium ions inside the neuron than outside. Second, the resting membrane potential depends on the differential permeability of the plasma membrane to sodium and potassium ions. Leak channels in the plasma membrane allow sodium and potassium ions to diffuse or leak down their concentration gradients. The membrane contains many more potassium leak channels than sodium leak channels. Thus, the membrane is much more permeable, or leaky, to potassium ions. As positively charged potassium ions leak out of the neuron, the inside surface of the membrane becomes negatively charged compared to the outside surface. If potassium was the only ion moving, the potential would stabilize at -90 millivolts. However, positively charged sodium ions leak into the neuron, which slightly offsets the negative charge and raises the voltmeter reading to -70 millivolts. Sodium-potassium pumps actively transport sodium ions out of the neuron and potassium ions back in, compensating for the sodium and potassium leaks. Thus, the pumps help to maintain the resting membrane potential.
Okay, so as you learned in the video, the membrane is much more permeable to potassium than it is to sodium, okay? 25 times more, which is one of the reasons why changes in potassium levels inside and outside the cell have a more dramatic impact on the membrane potential than changes in sodium levels do, okay? So if for some reason our total extracellular sodium were to rise significantly, that would have less of an impact on resting membrane potential than if our total potassium were to rise or fall dramatically, okay, because of the fact that this is a more permeable barrier to potassium. And this is one of the reasons why we have to take special care to make sure that our potassium levels stay within a nice tight range, whereas the sodium levels have a wider range through which they can vary, okay? Sodium diffuses into the cell down its concentration gradient through its leak channels, and potassium diffuses in the opposite direction, okay? The membrane is also extremely permeable to chloride, and it turns out that most of the chloride ends up outside the cell because the outside of the cell has a greater positive charge. More potassium diffuses out than sodium in, and that helps to establish the negative state inside the membrane. And the pump stabilizes this potential by burning a single ATP for each of 3 sodiums it kicks out and 2 potassiums it kicks in. Okay, so you can think of this leakage as constantly going on across the membrane, If nothing were counterbalancing that leak, then eventually the membrane potential would vanish, right? And there would be no potential difference in the membrane and no potential energy there. And so we couldn't use it to do any work. So in order to keep that separation going, we have to counterbalance that leakage by running this pump all the time. And it takes 3/4 of the ATP in the body to run this pump, and it also generates quite a bit of body heat. So you can see how the cycling works, right? For every ATP we bind, we're going to kick out 3 sodiums, and then we're going to pull 2 potassiums in, okay? The leakage will be going on all the time, but the leakage with the potassium is greater than the leakage with the sodium, and so what happens here is that the pump is counterbalancing all of this, okay? And the result then is that we maintain that charge separation, in addition to the fact that large negatively charged ions are trapped in the cytoplasm and can't get out, most of these being proteins. The membrane potential is going to change when we pop some of these gated channels and allow ions to flow. The changes can generate either a graded potential or an action potential. All right. Now, a graded potential is going to be proportional to the magnitude of the stimulus and will fade with distance, and can either be excitatory, meaning more likely to generate an action potential, or inhibitory, meaning less likely to generate it. Okay? An action potential moves at one speed, one direction, and one magnitude from where it's produced to where it stops. Okay? You can make graded potentials on the dendrites and the soma of the nerve cells, the neurons, but you can only make action potentials from the axon hillock on down to the axon terminal. And that's because of the composition of the membranes in those two parts of the cell being different. Okay? Changes in membrane potential are utilized as signals to receive, integrate, and send information. All right, so this is how we turn stimuli into electrical information, how we send that electrical information to the central nervous system, how we integrate that electrical information with other electrical information, and how we issue commands based on that information in order to respond to those stimuli in a way that keeps us alive. That's basically the role of the nervous system. Okay? Terms describing membrane potential are relative to the polarized state. A depolarizing stimulus is going to make the potential difference less across the membrane. So the inside of the cell will become more positive, or we could also say less negative. All right. So how might that happen? Well, sodium could flow in, all right, or we could have a net flow of a negative ion out, okay, such as a chloride channel, say, all right. So those are two ways that we can depolarize, all right. So you can see in a depolarization, we move closer to a zero voltage across the membrane. Okay, see how the little peak pops up there in the wake of the stimulus. Okay, so you can pick that up relatively easily. All right. Okay. Let's just go to arrow. There we go. And back. All right. In hyperpolarization, what happens is that the inside of the cell will become more negative. All right. So this can happen as a result of more potassium leaving the cell, right? Or more chloride entering the cell, okay? Or some other anion entering the cell, okay? The other way this can happen is by reducing the amount of positive charge that's flowing in across the leak channels, okay? So those are all ways to hyperpolarize something. Until you can see what a hyperpolarization looks like. So a hyperpolarizing stimulus is going to make it less likely that an action potential can be produced, and a depolarizing stimulus is going to make it more likely. Now, you might wonder, well, does a single stimulus result in the production of an action potential or not? And the answer is no. What we're going to find is that these graded potentials flow just like ripples on a pond, and they'll hit each other, and in some cases they will add together, and in some cases they will subtract, and that current flow will eventually make it to a region of the neuron called the hillock, where we're going to decide whether or not to generate an action potential. If we get to what we call a threshold voltage at the axon hillock, which is where the axon basically stems off of the soma, then we will make an action potential. And if we don't, we won't. Okay? So it's the summary of all of these small graded potentials that are being produced on the dendrites and the soma, and having them run into each other like ripples on a pond, that results in some effect on the hillock. All right? If we make it to threshold, we fire. If we don't, we won't. Okay? So the nerve cell, remember, is living in a nest of other cells that are talking to it all the time. The soma and the dendrites are constantly in these chemical conversations with the axon terminals of other neurons that are giving them these chemical signals that are either depolarizing or hyperpolarizing, right? And it's the net effect of those that results in either the production or the lack of production of an action potential. And you can see here that with a graded stimulus, you're going to flow from where the stimulus is generated away from the stimulus, and as you do, what will happen is that the effect of that flow will be diminished because of resistance. Okay? And the resistance in this case is essentially the current running into charges that may repel it. Okay? And so here's an important principle to keep in mind, right? That resistance to current flow in a living cell is in part due to the diameter of the region that's being stimulated. Okay? So the greater the diameter, the more surface area you've got, the less likely these charges are going to interfere with each other on either membrane, right, the top or the bottom of the cell. Okay? So another way to look at that is that the wider the barrel, or the thicker the cell is, that the more easily the current can move. Okay? In a graded potential, however, because we don't have these special types of membrane proteins that allow action potential to be produced, we eventually fade out when we get a certain distance away from the stimulus, and so the effect decays. All right? So if the effect decays, you might ask, well, then how is it that we eventually have an effect on the hillock? And the answer is through two different mechanisms, right? Through either what we call spatial or temporal summation. So what happens here on the dendrites and the axons is that we can stimulate many locations at the same time with a graded potential, and those currents can add together and flow to the hillock. Or we could pound on one region of the soma or a dendrite over and over again and produce current that flows further as a result. Or we can combine those two, okay? And it's the effect on the hillock that matters, right? Nothing else is going to make a difference other than either reaching or not reaching the threshold potential once we get to the hillock. Action potentials are long-distance electrical signals that go at one speed, one direction, and one magnitude from where they're produced to where they stop. And they only occur on the membranes of muscle cells and the axons of neurons, from the hillock on down to the axon terminal. And that's because of the composition of the membrane in those regions, right? They have these special types of membrane proteins that let action potentials happen. In an action potential, we see a reversal of membrane potential with a change in voltage of about 100 millivolts. These signals don't decay over distance like the graded potentials do, And this is always an excitatory signal, okay, meaning it's going to produce an effect once it gets to the other end of the axon. So gated channels in areas of the cell that are capable of generating an action potential have doors on them that when they're closed don't allow ions to flow through them, and when they're open they do. Okay, so each sodium channel has two voltage sensitive gates. There's an activation gate and an inactivation gate. The activation gate is closed at rest and opens with a depolarizing stimulus and lets sodium flow into the cell, while the inactivation gate is open at rest and blocks the channel once it is open to prevent more sodium from entering the cell. Okay? So if either one of these doors are closed, no flow will happen. Okay? It's like having a door in your house that has an inside screen door or an outside screen door and a main door, right? If either door is closed, you can't get into the house. The potassium channel has one voltage sensitive gate that's closed at rest and only opens with depolarization. Okay? So the sequence of events in an action potential, and remember this is only happening from the hillock on down to the axon terminal, is that we have a stimulus. That stimulus, which would be in this case the sum of graded potentials getting to the hillock and pushing us to what we call threshold voltage, which is minus 55, causes the opening of the activation gates of sodium. Okay, so what will happen here is that those gates will pop. The inactivation gates are already open. Okay, so we just open the activation gate and the sodium flows into the cell, and that causes a depolarization up to positive 30 millivolts. And at that point, two things happen. The inactivation gates on the sodium channels close, and the activation gate, which is the only gate on the potassium channels, open. Okay, and then what happens is that potassium is going to flow out of the cell and result in that region of the membrane repolarizing and even hyperpolarizing. And then the action of the leak channels and the pumps will bring everything back to the threshold voltage. Okay. Now, what will happen once we get to the threshold voltage on this side, right, where the dotted line is that the sodium channels will be back in the state they were before we generated the first action potential spike, right? So what will happen is the activation gates will shut, right? And the inactivation gates will be open at this point, which means theoretically that a strong enough stimulus could come at this point and cause another action potential in that section of the membrane to happen. Okay, and this is called the absolute refractory period. So it goes from where the threshold voltage hits here to where the threshold voltage hits here. Okay, and it's important because it causes the action potential to move in only one direction. Okay, by the time we get back to the point where the sodium gates could be restimulated, the action potential that just passed that part of the membrane has moved on to the next part of the membrane and can't flow back in the opposite direction because of this absolute refractory period that spans from here to here. Okay, and you can see the sodium permeability in this, right? When we hit that threshold potential, it spikes up, right? And then we slam shut when we get to that voltage, and then the sodium permeability is dropping, dropping, dropping again. At this point, a strong enough potential could reopen those sodium gates, right? Which would be here on the action potential. So that would be the length of the absolute refractory period, right? In muscle cells, that's really short, okay? And it's so short that you can produce a series of action potentials so close together that the muscle fibers don't get a chance to relax between signals that result in contraction, and that produces something called tetanus, right? Which is a sustained contraction that eventually exhausts your energy stores, and then the muscle can't do the work anymore and goes into fatigue. Okay, it's pretty short for the axon as well. Okay, um, and it's the length of this absolute refractory period that determines how closely together action potentials can be produced on that nerve cell. Okay, very important. In the resting state, all of the sodium and potassium channels are closed, and only the leak channels for sodium and potassium are open, and this maintains the resting membrane potential. Depolarizing local currents open voltage-gated sodium channels, and sodium rushes into the cell. This movement causes more depolarization, which opens more sodium channels and causes the intracellular fluid to get less negative, and then at threshold, that magic voltage, positive feedback causes all of those sodium channels to pop, and then we zip up to positive 30 millivolts in that section of the membrane. Okay, that's the action potential spike right there. Okay, so if you don't get to that magic voltage, that spike won't happen. Okay, if you get to that voltage, that spike is going to occur, and that potential is going to move from its origin to its destination. No stopping it. Okay. In the repolarizing phase, the sodium channels inactivation gates will close. The membrane permeability to sodium drops back to resting state, and the AP spike stops going up. And the voltage-gated potassium channels open up. Potassium exits the cell, and we go back down as we repolarize and then hyperpolarize below threshold voltage. Okay. Some potassium channels remain open, so the extra potassium flowing into the cell results in the hyperpolarization, which is the dip below the resting voltage, and the sodium channels are beginning to reset at this point, right? So they're going back to the time when the activation gates are shut and the inactivation gates are open, okay? And that was on the other side of the spike where I showed you. So the next video is going to tell you how an action potential is generated, okay, and where that happens and why. All right, so stay tuned.
Neurons send signals over long distances by generating and propagating action potentials. Most action potentials originate near the axon hillock of the cell body, in the initial segment of the axon. It then travels the entire length of the axon. A closer look reveals that during an action potential, voltage-gated channels open and close, altering the permeability of the plasma membrane to sodium and potassium ions. A threshold stimulus changes the shape of the voltage-gated sodium channels, causing their activation gates to open. This event marks the beginning of phase 1 of the action potential, known as depolarization. As sodium ions diffuse into the axon, the membrane potential becomes less negative. This causes more voltage-gated sodium channels to open, and the membrane potential soars to plus 30 millivolts. At this point, two key events occur. The inactivation gates of voltage-gated sodium channels close, and voltage-gated potassium channels open. These two events mark the beginning of phase 2 of the action potential, known as repolarization. As potassium ions diffuse out of the axon, the membrane potential becomes negative again. However, the membrane potential continues in the negative direction, going beyond the resting state of minus 70 millivolts. This marks the beginning of phase 3 of the action potential, known as hyperpolarization. During this phase, voltage-gated potassium channels close and all voltage-gated sodium channels are released from inactivation. By the end of this phase, ions move through leak channels only and the membrane potential returns to the resting state of minus 70 millivolts. The neuron is now ready to fire another action potential. Summary: generation of an action potential. A threshold stimulus opens voltage-gated sodium channels. Sodium ions diffuse into the axon, depolarizing it to plus 30 millivolts. Voltage-gated sodium channels close, and voltage-gated potassium channels open. Potassium ions diffuse out of the axon, repolarizing it to a negative value. The membrane potential briefly hyperpolarizes. Voltage-gated potassium channels close, and the membrane returns to the resting state of minus 70 millivolts.
So the sodium-potassium pump is responsible for two things, really. It restores the ordinary distribution of sodium and potassium across the membrane after the action potential has passed. Okay. It also restores the normal distribution of sodium and potassium across the membrane after a graded potential is passed in the soma or on the dendrites. Okay. So it's like a mop-up, and it's always running all the time. All right. So once the action potential goes past a segment of membrane, the leakage of ions across the membrane and the operation of the pump will reset that membrane so that another action potential can be generated. Okay? And this only takes a fraction of a second. Not all depolarization events are going to generate an action potential, right? And we discussed the fact that if you don't get to threshold voltage at the axon hillock, you're not going to produce that action potential. You're going to end up basically not producing a signal. Okay? If you approach or exceed the threshold voltage, then you will generate that action potential. Okay? At threshold, the membrane is being depolarized around 20 millivolts. The sodium permeability goes up. Sodium outflow exceeds potassium flowing in, and that's eventually going to pop those voltage-gated channels, sodium channels, and result in the spike of the action potential. So the next little insert is going to tell you how an action potential is propagated.
Action potentials propagate in a continuous fashion in unmyelinated axons. Once an action potential is generated in the initial segment of the axon, it propagates the entire length of the axon. Recall that a threshold stimulus causes voltage-gated sodium channels to open. The influx of sodium ions generates an action potential. It also establishes a depolarizing current that flows to the next segment and brings it to threshold. Voltage-gated sodium channels open, regenerating the action potential in this segment of the axon. Current flows from this segment and depolarizes the next segment to threshold, thus regenerating the action potential yet again. In this way, regeneration continues in one direction all the way down to the axon terminals. The basis for unidirectional propagation is revealed when we take a closer look. By the end of the depolarization phase of the action potential, all voltage-gated sodium channels inactivate and voltage-gated potassium channels open. These two events render this segment of the axon temporarily insensitive or refractory to another depolarizing stimulus. However, voltage-gated sodium channels in the downstream segment are closed and receptive to a depolarizing stimulus. Thus, propagation occurs sequentially down the axon to the axon terminals. In myelinated axons, action potential propagation is a bit different. Here they propagate in a saltatory or leaping fashion. The myelin sheath consists of multiple layers of tightly wrapped glial cell membrane. But this sheath is not a continuous one. Exposed areas of axonal membrane, known as nodes of Ranvier, occur at discrete intervals. Voltage-gated sodium channels are abundant in the nodes, but largely absent between nodes. So, action potentials are regenerated at each node, not in areas covered by the myelin sheath. However, the myelin sheath does provide the insulation necessary for the rapid spread of depolarizing current. And the sooner the nodes reach threshold, the faster action potentials propagate along the axon. Saltatory conduction is extremely fast. Velocities often exceed 100 meters per second. In contrast, continuous conduction is fairly slow. Velocities rarely exceed 2 meters per second. Nevertheless, both continuous and saltatory conduction propagate action potentials over varying distances because action potentials regenerate along the way. Summary: propagation of an action potential. Once generated, the action potential propagates the entire length of the axon without decrement.
Okay, now one of the questions you might have then is, since all action potentials are the same magnitude and um, are always going to move at a particular speed, then how is it that we interpret in our brain a strong versus a weak stimulus? And the answer to that is relatively straightforward, okay? It has to do with the frequency of the action potentials. The more frequent the action potentials are, the more strongly the stimulus is interpreted in our brain. And the less frequent they are, the less of a stimulus is interpreted in our brain. It's the same with a command that's sent, right? If we send a command, say, to a muscle or to an organ, right? The more rapidly we produce the action potentials that hit that target, the greater a response we're going to generate from that target. And the fewer action potentials we produce per unit time, the less of a response we're going to get. Okay, so that's the stimulus intensity. It's all the rat-a-tat-tat. So if the rat-a-tat-tats are real close together, right, that's a strong signal. If they're far apart, that's a weak one. Okay, so it's the number of impulses per second. The central nervous system is going to determine the intensity by the frequency. Higher frequency, stronger stimulus. Okay, so you can see here some differences in voltage, right? This is just a voltage generated across a membrane, say with an electrode, something that artificially generates a current. And you can see here that below threshold, we don't do squat, right? No firing. We reach threshold, what do? We generate action potentials that fire at a particular frequency. Now, the stimulus strength will determine how long that section of the membrane, let's say the hillock, is going to stay at or above threshold, right? The stronger the signal, the longer we're going to stay above threshold, the more frequently we can open those sodium gates and fire those action potentials. See the strong stimulus here? Bang, 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 one right after the other. That's a strong enough stimulus, i.e., enough graded potentials flowed to the axon hillock and pushed it significantly above threshold, that we could produce a big volley of action potentials rocketing from the hillock down to the axon terminal and resulting in neurotransmitter release. Okay, you're probably looking at, with something like this, the most intense or the highest rate that we could send the action potentials at. So that's probably the intensity limit of the axon at that point. You're probably bumping these things right up next to each other, spaced apart, just about equal to the absolute refractory period. Okay. So when voltage-gated sodium channels open, the neuron can't respond to another stimulus, right? Because in order to activate voltage-gated channels, you have to open the activation gate. And the activation gates are only going to be closed if we get back down around that threshold voltage around 55, okay? In the absolute refractory period, what we have is the time from the opening of the sodium channels until they reset. And that's basically on either side of the peak, right about where the threshold voltage is. And this allows each action potential to be, number one, an all or none event, but more importantly, it forces the action potential to go in only one direction, okay? Because during the refractory period, the current can't back up and go back towards the hillock. The relative refractory period is a different animal, and it comes after the absolute refractory period. Most of the sodium channels have returned to their resting state, so the activation gates are closed and they can be opened with a stimulus. Some potassium channels are still open. Repolarization is occurring. The threshold for an action potential here is a little bit higher, so a strong stimulus could produce an action potential. And if you look at this diagram, you can see where they're located, right? See how short the absolute refractory period is? And it's basically on either side of the peak, right around where threshold would be, okay? Right around where threshold would be. And the hyperpolarization, right? The time from where the blue picks up here, right? And the yellow ends. This is the end right here. Let me circle it. Okay. This right here would be the end of the absolute refractory period. All of this is relative refractory period from here to here, okay? And a strong enough stimulus will produce another action potential in this region. So theoretically, if your stimulus was strong enough, you could generate another action potential right where I've circled, okay? But the resting state is going to be out here at this point, right? Once we're back to our original resting voltage at minus 70. And it's the leak channels into pumps that accomplish that for us. The velocity of an action potential, the speed of an action potential, can vary from 5 miles an hour to 250, okay? And what determines the speed of the action potential, as you learned in the previous video, is the diameter of the axon. The wider the diameter, the faster the conduction velocity. And that's because the broader the barrel, the less interference to current flow you've got, because what's happening on one side of the barrel is far enough away from what's happening on the other side of the barrel that they don't run into each other, okay? And the other thing that speeds up the action potential, as you know, is the myelination. The myelin wraps around the axon and produces regions called internodes that have very little leakage. And when there's no leakage, the current moves under the insulated portions, the internodes, very rapidly, which means that the depolarization of the next node to threshold and the production of that next action potential happens much sooner. As a result, the fastest neurons are going to be the wide barrel, highly myelinated type, okay? And those are the kinds we see in the somatic motor division that talks to our skeletal muscle, and the somatosensory division that brings information in from our muscles and our joints so that we know how to keep our balance when we're moving, okay? The degree of myelination determines the conduction type, right? Continuous conduction occurs across every square inch of the membrane, and that would be in an unmyelinated axon, whereas saltatory conduction appears to leap from node to node, when in fact what's going on is that you're producing an action potential at the node, and then you're pushing current under the inner node and generating a next action potential at the next node more quickly, okay? So the myelin sheath is critical to speeding up the action potential. If the entire sheath were myelinated and there were no gaps, then the current would eventually fade and not make it to the end of the axon, okay? Whereas with those gaps, right, you can speed up the action potential by producing subsequent action potential spikes in those nodes. Now, in the event that the myelin sheath were destroyed, and there are diseases in which that happens, such as multiple sclerosis, okay, what will happen is that the resistance in the axon will become so great that the action potential won't reach the end of the axon, and we won't generate a signal to talk to the next target in the pathway, which could be a muscle cell or could be another neuron or anything, okay? In MS, when that happens, it affects primarily the central nervous system, and it affects the neurons that bring information from the brain down through the spinal cord to what we call the peripheral nerves, which head out from the spinal cord and go to the muscles. So what happens is the connection between the brain and the peripheral nerves is kind of like rusting out. And the result then is when you want to make a movement, it's very difficult for you to do that. Okay? It's the result of an immune attack on the myelin sheath in the central nervous system, in which our own immune system has somehow broken through the blood-brain barrier and destroyed that insulation, and that results in what we call the upper motor neurons losing function after a time. And so what you see in MS individuals is loss of motor coordination, loss of muscle tone, okay, and eventually down the road it could result in paralysis. So the myelin sheaths insulate and prevent leakage of charge and promote that saltatory conduction, which gets you up to about 250 miles an hour top speed. Okay, the action potentials are only produced in those physical gaps between where the myelination occurs, and so the signal appears to jump rapidly from gap to gap. But what's actually happening, as you see here in this example of a myelinated axon, is that we're popping the action potential here, and the current is going zip to the next node, and then we pop another action potential, and then we go zip to the next node all the way down to the end, right? And we move real quick under here because the myelin lets the current flow faster and more effectively to its next target, which in this case would be the gap between the two myelin sheaths. And so enough of that gets there that we can pop that new action potential, right? So this is why I said that it's the distribution of these membrane proteins that lets an action potential happen in the first place, right? You can see in a non-myelinated axon, you still have the ability to regenerate action potentials all along the axon. The spacing here is closer because you don't have the myelin, and so the current fades with distance more extremely, which is why you need nearby voltage-gated sodium and potassium channels in order to make that action potential be recreated a short enough different distance away that the signal will continue. Okay, and these gates simply aren't present on the soma and the dendrites. Right, the situation on the soma and dendrites is up here. Right, you generate a stimulus and you fade with distance. Right, because again, you don't have the ability to reproduce the stimulus as a result of voltage-gated membrane channels. They're not present here, okay? So it's only from the hillock on down to the terminal where this can happen in a nerve cell, okay? Or on the membrane of a muscle cell. And there's MS, right? The immune system moves in, it destroys the myelin sheath, and the result is that we lose the ability to talk to our target, which is skeletal muscle. Okay. We also see visual disturbance, speech disturbance, urinary incontinence. We can use immune suppressants, okay, but that's not going to necessarily stop the progression of the disease. How to prevent it, we honestly don't really know, okay, to be blunt with you. Vitamin D may play a role. We're not really sure. But what we do know is that the immune system has somehow gotten in to the central nervous system and is causing these problems. Now, we talked a little bit earlier about nerve fibers, right? That there are different speeds to carry out different tasks, okay? And there they are, right? You've got the group A fibers, which are the large diameter myelinated. They kick the signal down at 250 miles an hour. You've got the group Bs that are about 25 miles an hour. And then you've got the group Cs that are going to be around 5 to 10 miles an hour, okay? Now you might wonder, well, why don't we just use group A for everything? That's a fair question. And the answer is that it would be an unwise use of resources and energy, okay? Because it takes more energy to produce and maintain group A fibers than it does B and C. And so we preserve the group A fibers for the high speed work that needs to be done, which is us talking to our skeletal muscles so we can move, and us getting information about our body's position in space while we're moving, which is from our somatosensory fibers, okay? The other fibers are found in things like the autonomic nervous system and as part of our special senses, okay? And those speeds don't have to be nearly as rapid and still get the job done, all right? So it's just a prudent use of resources. Okay, I'll see everybody in the Chapter 12 podcast, and have a good evening.